All right, welcome back, everybody. So hopefully the exam redos are going along pretty well. As a reminder, you can always come talk to me for questions about it and to get help on it if you are struggling with any of the problems. We had our pre-lecture on 2.3. Hopefully you watched it. It's on polynomial division and the factor theorems. The pre-lecture was just on the two different techniques that we will be using, which is polynomial long division, which you might have seen before. And if you have, awesome. If you haven't, no big deal. That's what we're doing here. And so the key way it works is that it is going to be that if you take a polynomial, p of x, called your dividend, and you divide it by d of x, your divisor, it can equal your quotient plus your remainder divided by your divisor. And it works just like the old way of doing regular long division with numbers. The only difference being that now we're dealing with polynomials instead of this. There's a little bit of nuance that changes. So it's still the same idea of how many times does this go into this, figure it out, multiply, put it down here, subtract, and so on and so forth. One of my favorite things when I first moved here, I was teaching a lot of the night classes, and um, I was teaching at the Silo campus at CS at Palo Verde High School, and there when we came out, I had a big like because I didn't have an office at that point, I had a big stack of my books that I was carrying everywhere. And there was this young boy and his grandmother, and they saw me saw my wife and I carrying our big textbooks and stuff, and they said, "Are you a teacher?" Like, yes, I am. What type of stuff do you teach? Teach math. Do you want to know how long division works? It's like, well, yes, I would love to know how long division works. And he explained the whole process. And I asked him, just because I'm a teacher, I was like, and why does that work? And he said, because my teacher told me so. And good answer. Good answer, kid. Don't need to know anything else besides just do what the teacher tells you, right? Now, of course, there is a reason why it works, and I'm happy to show you the old fashioned way if you'd like to know. But so for this one, the key thing is unlike with regular long division, you need to make sure that all powers of your variable are present. So in this case, all powers of x are present in the dividend. So 14x squared, one less is 9x, one less is the constant term, and it has all of them. So we don't need to put any placeholders. We'll see an example of that in a moment. Then what you are doing is essentially saying how many times does 7x go into 14x squared? Um, and the answer is it's 2x because if you multiply 7 by 2, you get 14. And if you multiply x by x, you get x squared. Then what you do is you multiply this number that you found into your divisor, and you get 2x times 7x, that's 14x squared. 2x times -1, that's minus 2x. Now, I frequently, when I do this, I write this in a different color. This is all in different colors, yes, but even when I'm doing it myself on exams and stuff, even in my own grad school classes, I would still do that because I never trusted myself to remember if I don't write the parentheses, it just looks like I'm subtracting 14x squared and also subtracting 2x. But as we saw in the pre-lecture, this minus sign gets distributed. So this is really a plus 2x because it's subtracting a negative 2x. That's why I get -9 minus negative 2x. That gives me -7x. And then I bring everything down that I can and then do the whole process over and over and over again. So uh, how many times does 7x go into -7x? It goes into it -1 times. -1 times 7x minus 1 is -7x plus 1. But now I'm subtracting that. And so the -7x's cancel. 2 minus +1 is 1. So there's a remainder of 1. And the reason why that's the remainder is there is no nice way for 7x to go into 1. There's no way, there's no power of x that I can multiply 7x by to get 1. I'd have to go into negative number. I'd have to go into negative exponents, which we don't want to do. And so at the end of the day, that tells us that our division is equal to our quotient plus our remainder divided by our divisor. That is how we will write it. Now, as it says up here, this is the traditional way to see the division algorithm written. So if you plan on becoming a math major, which I don't recommend, it's a bad idea. But if you do want to, that's the way you'll probably typically see it because that's much better for proofs. But it has a few applications to us here and there, but for the most part, this is what we're going to be doing. Okay? Any questions on long division? Let's do some practice. So we've got this first one. It says 27x cubed plus 9x squared minus 24x minus 10 divided by 23x squared minus 2. Now it doesn't so if you notice the dividend, the thing that's going to get divided, it has every power of x present. It has an x cubed, then it has an x squared, then an x, then 10. But the divisor, 3x squared minus 2, it doesn't have an x to the first power term. That is okay. It's not the end of the world, but you can write a placeholder if you want, but it's not really necessary for the divisor. You'll see why it's necessary for the dividend. But you can write it if you want, but it's not required. But so anyways, 3x squared minus 2 divided into 27x cubed plus 9x squared minus 24x minus 10. And so we do this just like we did before. We ask ourselves, how many times does the leading term of our divisor, so 3x squared, how many times would that go into 27x cubed? And the more you do this, the better you get at answering it and saying that the answer is going to be 9x. But if you don't see that right away, that's okay. You can just go off on the side and do 27x cubed divided by 3x squared. You'll see that the 3 and the 27 cancel a little bit, leaving with a 9. And the x squared cancels out 2 of the x's, leaving you with a 1x. Or an x to the first power, that is. So that's why it's 9x. But the more and more you do this, the better you get at it. And in case you're thinking like, please God, I've seen this before. I don't want to do this ever again. I'm just going to try and put this into my short-term memory, save it for the exam that comes up, and then just put it out and call it good. Sadly, this shows up again and again and again and again in your mathematical career. Not very common, but it will keep showing up. So it's kind of like you got to treat it like a bicycle. You got to kind of just memorize it once and very with minimal reminders, you'll be able to ride the bike again. So anyways, any questions on how I got 9x? Now that I figured out how many 3x squareds go into 27x cubed, I will multiply them. By the way, you can put this here, which is where I'm putting it in right on top of the x to the first power term, but there's nothing stopping you from putting this over here or over here. This is just convention. So 9x times 3x squared, that's going to be 27x cubed. And then 9x times negative 2, that's negative 18x. And I'm going to put that where the x term is. I don't want to get it confused. I don't want to put it under the x squared term because that will make it look weird. Because it's not like I'm not subtracting it from the x squared term. I'm subtracting it from the x term. Then I subtract. Those cancel kind of by design. There's nothing to subtract the 9x squared from, subtract from the 9x squared. So it just comes along. It becomes 9x squared. And then, is it going to be 30? Is it going to be 42 or is it going to be 6? Is it going to be negative 42 or negative 6? Negative 6. So remember, this minus sign, the reason why I've written it in red is to remind myself that this gets distributed into both. So this now becomes a plus. So it's negative 24x plus 18x, which is which leaves you with negative 6x. And then bring down the minus 10. Next, we ask ourselves, how many times does 3x squared go into 9x squared? And it goes into it 3 times. So we write a +3, a +3. And then we do the multiplication here. So 3x squared times 3, that's going to be 9x squared. And then 3 times -2, that's -6. And I'm going to put that under the constant term, not under the 6x, because I need to be subtracting the constant term. And then, oh, I forgot to, I meant to write that in red. So we're going to subtract this from that. 9x squared minus 9x squared, those go away. There's nothing to subtract from the -6x, so it just comes along. It just goes down. -6x. And then will I have -10 or will I have -16 or -4? -4. Because it's going to be -10 minus a -6. That's really +6. So -4. And this is where I stop because there is no way to put 3x squared into 6x evenly. So that's going to be where I have a remainder. This is my divisor. So my final result, if I want to write it as quotient plus remainder divided by divisor, is to write it as 9x plus 3 plus our remainder, which is -6x minus 4, over our divisor, which was 3x squared minus 2. Any questions on that? All right. So the next one, 3x cubed plus x plus 5. Notice that the dividend, the thing on top, the thing that's going to get divided, it doesn't have an x squared term. So note, no x squared term. So we need a placeholder. What do I mean by that? So remember that 0 times anything is 0, and you can always add 0 to any expression and it doesn't change anything. So what we're going to do is we're going to rewrite this as x plus 1 divided into 3x cubed plus 0x squared plus x plus 5. And I have a very good reason to, a very good way to justify this to you. If this seems weird, why do I have to do that? Why do I have to put it plus 0x squared? Short answer is you don't, technically. However, I can tell you from experience that you will get it wrong 99% of the time if you don't. And here's a better reason to understand why. Notice in this previous example, don't worry, I'm coming right back. In this example, I chose 805 for a very, very specific reason. It doesn't have any tens in it, right? It has 0 tens, 8 100s, 0 tens, and 5 ones. Do we still write the 0 when we're doing the long division? Yes, we still do because it still plays a role. It's a digit and it plays a role in the division. So much like the 0 and the 10 spot, the x squared is kind of like a digit in that polynomial as a number, quote unquote. So the 0x squared has to be there because it's one of the digits. That's the idea. So now that we've got that, we have everything we need to do. We ask ourselves, how many times does x go into 3x cubed? It goes into it 3x squared times. So we'll get 3x cubed when we multiply the result up here by our dividend. 3x squared times x plus 1, that's going to be 3x cubed plus 3x squared. So we'll subtract that. Bless you. And what do we get? in that subtraction. Just a negative 3x squared. And we'll bring down the x and the 5. I'd like you guys to finish the rest of it yourselves, and we'll slowly fill in the I'll slowly fill in the details. So people watching the recording, pause it and complete it. You can unpause it to check for work as we go along. Okay, so we should get this. Are there any questions on how I did it, or would anyone like me to go over the process? Okay, cool. So once we had done this, we had subtracted it, and we've got negative 3x squared plus x plus 5. We ask ourselves, how many times does x go into negative 3x squared? Well, it goes into it negative 3x times. Because if you multiply negative 3x times x, you get negative 3x squared. So we'll go ahead and multiply that in. We get negative 3x squared minus 3x. And then when we subtract that, these cancel, and that's by design. That's by construction. And then we have an x minus a negative 3x. That's really x plus 3x. That's where I get the 4x. And then we do the process over again. How many times does x go into 4x? It goes into it 4 times. And then we multiply 4 times x plus 1, getting us that 4x plus 4. And subtract. The 4x's cancel. 5 minus 4 is positive 1, leaving us with a remainder of 1 because x no longer goes nicely into 1. There's no way to get multiply 1 by anything to get, or divide it 1 by x to get anything that's nice. So our quotient is up top, 3x squared minus 3x plus 4, plus our remainder divided by a divisor, so that's 1 over x plus 1. Now, before we go on to the great news at the bottom, I wanted to make an observation between the degree of the quotient. The degree of the quotient up top was degree 1, and the degree of the quotient here was degree 2. The degree of the dividend was degree 3, and the degree of the dividend, the divisor, was 2. 3 minus 2 is 1. Similarly, degree 3, degree 1, the difference between those two degrees is degree 2. This is not a fluke. This happens every time. So the degree of the quotient equals the difference of degrees of dividend and divisor. So the difference between those two things, the top and the bottom, the difference between the two degrees will always give you the degree of the quotient. And that plays an important role because when we talk about synthetic division right after this, that will explain better why the answer was the way it was. Any questions on that? The degree of the quotient will always be the difference between the two degrees. Okay. Now, one of the cool things about mathematics, one of my favorite things about math in general, is that you can always check your work. You can, well, I mean, not always, but a lot of the time you can check your work. And a lot of the times it's something nice and straightforward. If you want to check to make sure that your division is correct, undo the division by doing multiplication. If you multiply your if you multiply your answer by your divisor, you should get back your dividend. So if I take this entire thing and I multiply it by x plus 1, I should get back to 3x cubed plus x plus 5. And we'll see that right here. So if I take x plus 1 and I multiply that into 3x squared minus 3x plus 4 plus 1 over x plus 1. Now remember, I've got to distribute this into all of these terms. So that gives me 3x squared times x plus 1 minus 3x times x plus 1 plus 4 times x plus 1 plus 1. Because remember, when I distributed into the last term, the 1 over x plus 1, the x plus 1s will cancel. Continuing onwards, that'll give me 3x cubed plus 3x squared minus 3x squared minus 3x plus 4x plus 4 plus 1 when I take care of all the distributions. So when I distribute the 3x squared into the x plus 1, that's where I get the 3x cubed plus 3x squared. Then I get the minus 3x squared minus 3x by distributing in the negative 3x into the x plus 1, and so on and so forth. And the 3x squareds will cancel. The negative 3x plus the 4x gives me 1x, and the 4 plus the 1 gives me a 5, which gives me 3x cubed plus x plus 5, which is precisely our divisor, our dividend, excuse me. So you can always check your work. You've got that in your back pocket. Yes, it does take time, absolutely, but it's one of those things. At the end of your exam, if you have a little extra time, might as well go through and check to make sure that it all worked out. Never hurts to do so. Okay. Onwards to synthetic division. So it's as my pre-lecture said, it's a really, really quick option. It took us a long time in the video, but that's only because we were explaining every step. You'll see how fast it can be. I'm going to show you how fast you can get at it in the next problem. But the way it works is you can only do this if your divisor, the thing that you're dividing with, is of the form x minus a number. So this situation here, the example works because even though it says x plus 2, you can get that into the proper format by double negating, writing it as x minus negative 2. So the way, but it wouldn't work with something like x squared minus 5 because that's not x minus c, that's x squared minus c. And it won't work with 2x minus 1 because even though it has a minus c, it's not 1x, it's 2x, that's the problem. Now, that might seem like this is a very, very niche situation that won't be applicable to many things. And that's true. It only works for this situation. However, we'll see in just a moment why we care about this method. And I will send out a video later today. And I haven't posted the pre-lecture for next week, for next Monday, but I will be posting it soon. But I'll also send out a video explaining how synthetic division works, why we can do all this weird stuff and it works out. Because it does. You can, like, if you don't want to learn long division, or if you don't want to learn synthetic division, you don't have to. You can still just learn long division and get through the whole thing. It's just this is faster for most things we'll be dealing with. So the way it gets set up is you write you write your C value here and the coefficients of all of your dividend up here with your constant term right after the bar, the vertical bar. The first step is to then you bring down the first term, and then after that, you multiply the terms together and put them in the next spot in the green space. So negative 2 times negative 1 or times 1 is negative 2. I put that here. Then I add them vertically together. -7 plus -2 is -9. And then I repeat the process of multiplying diagonally, adding vertically until I complete the entire chart. So this was a degree 3 polynomial divided by a degree 1 polynomial. The quotient should be degree 2. 3 minus 1 is 2. And so that's how I figured that out. It's always like because with synthetic division, you're always dividing by a degree 1 polynomial, the quotient will always be 1 degree less. So if you have a degree 3 polynomial, you get a degree 2 quotient. If you have a degree 10 polynomial, you're going to get a degree 9 quotient, and so on and so forth. So, any questions on this method? Don't worry, we'll get plenty of practice. So this took a long time. Yes. Oh, yes.
If there's a coefficient for x on the divisor, would it still work? Or
If there's a coefficient on the x, like 2x minus 1.
right.
So it can work, but you have to be very clever about it. You have to it can only work if it's x minus c, but you can bypass that by writing 2x minus 1. You can write this as 2 times x minus 1/2. And you can divide by this and then divide the result again by 2. So you can do it, but it's not really recommended. All right. So to show you how fast it is, I'm going to show, we're going to go through this problem together, but I want to show you how fast I can do this division. Because imagine trying to do this with long division. That's going to take a lot of steps because that's a degree 4 polynomial. But with synthetic, check it out. So my answer is immediately, wait, I did change this. Yes. Let me make sure, so it's not in the same as my notes. So I want to check my work, but okay. Yep, that should be it. So the answer is going to be -7x squared minus 11x minus 2 plus -12 over x minus 1. Isn't that fast? Let's go ahead and work through it and explain it now again. So let's actually get there again. So our C value is equal to 1 because this is already in the proper format of x minus a number. And that number is 1. We're subtracting 1. So our C value is 1. So we set that up. 1 divided into, we're going to write -7x cubed. Notice that all the powers of x are present. There's an x cubed, there's an x squared, there's an x, and there's a constant. If there wasn't, we'd need to write a placeholder. We'd need to write a 0 for any of the x powers that are missing, but there aren't. So -7, -4, +9, and -10, and a bar right before the constant term. You always bring down the first term, so that's -7. Then we do 1 times -7, that's going to be -7. -4 plus -7 is -11. Right? We multiply diagonally, add vertically with synthetic division. 1 times -11, that's -11. Then we add vertically. 9 plus -11 is -2. 1 times -2 is -2. Then add vertically. -10 plus -2 is -12. So our quotient is -7x squared minus 11x minus 2 because it's going to be a degree 2 polynomial because it's degree 3 minus degree 1 plus our remainder, which is -12 divided by our divisor, which is x minus 1. So very fast. A very, very quick explanation as to why it's working and what we're doing is this is really, really synonymous. Say like in mathematics, if you decide to become a math major, you'll have to take a course called topology, which is a lovely course, but a lot of people don't like it. I understand why, but regardless, there's a thing that we study in mathematics called a homeomorphism. And what it means is that these two things are basically the same, just different. Um, like your phone, your like as a simple example, your phone and my phone, they are homeomorphic. There is a way for me to change everything in my phone to get it to be your phone. I'll have to delete some apps, maybe add some apps, but at the end of the day, I can morph my phone into your phone, right? So there is a homeomorphism between synthetic division and matrices. We won't get into matrices in this class, but matrices are a way to solve systems of equations very fast. So if I'm trying to solve x plus y plus 1 plus 10z equals 3, and then 2x minus 5y plus 7z equals 9, and 8x minus 3y plus z is equal to 9 as well. Trying to solve this, as we'll see in Unit 4, it takes a long time. But in matrix algebra, what you can do is you can convert this to 1, 1, 10, 3, 2, negative 5, 7, 9, 8, negative 3, 1, 9. So what I'm doing is I'm dropping all of the variables, right? I'm dropping all of the variables because those things take time to write. And so with matrix algebra, it basically gets rid of everything that you're doing. So I probably should have mentioned, don't go ahead and don't write this down. We'll talk about systems of equations later on, but not matrices. That's Math 253. Math 253. Very, very fun course. If you plan on going further into mathematics, like for whatever reason, whether you want to be an engineer or you want to be a math major, linear algebra is basically at the core of everything that you will ever do. So I want to let this be known. If you're planning on becoming an engineer, linear algebra is going to be used. Like, so if you plan on becoming an engineer or anything like that, you will use linear algebra. So don't blow it off. Don't think that you're never going to use it. You will. It's very, very important. It's everywhere. Okay. Any questions? So in short, the reason why synthetic division is faster is because you're just bypassing writing the variables. All right. So this next one, x squared, x to the fourth minus 2x cubed plus 3x squared minus 4. Notice that the power of x is missing. Note, no x to the first power term. Need a placeholder. We need to make sure that that digit is mentioned. So when we're setting up this synthetic division, what's the c value? Take a second. -3 is correct because needs to be in the format of x minus c. So I'm going to rewrite this as x minus -3. This is our c value. So -3 goes out here, and then we go ahead and set up the synthetic. So all the digits of the dividend, the thing that's being divided, go in this spot. So 1x to the fourth minus 2x cubed plus 3x squared plus 0x minus 4. And we put the vertical bar right before the constant term. So I'm going to start it off for us, and then I'm going to let you finish it. We bring down, like it's always that you bring down the first term. Then you multiply diagonally and add vertically. Multiply diagonally, add vertically, and complete the whole rest of the chart. Go ahead and do that. People watching the recording, pause it, and you should do it yourself. You might need a calculator. So this is our answer. We did this by multiplying diagonally and then adding vertically. We can always check our answer by multiplying by x plus 3. Any questions on that? Last one is a trick question. Notice that it's not of the format x minus c, so we cannot use synthetic division. So we have to do long division. Sad face. But it's not too terrible. There is a way to do synthetic division, but I would not recommend it. Because what you could do, if you're curious, you could write this as x plus square root 2 times x minus square root 2. And then you are dividing by an x minus a c. And so you just have to set up it with a c equaling square root 2, which is not fun. Do not do. Bad idea. But it can be done. Just not very fun. So either way, so we've got x squared minus 2. We can put a placeholder for the divisor, but it's not really necessary. And notice that there are a lot of missing powers of x. There's a missing x to the fourth, there's a missing x squared, and there's a missing constant term. So we need to put placeholders for all of those things. So 2x to the fifth plus 0x to the fourth minus 6x cubed plus 0x squared minus 14x plus 0. Now, it's not too terrible, and we're actually not going to finish it here. I'm going to let you guys do this on your own time. I want you guys to do this later today. Like, if you have a class after this, do it after your next class. If you don't have class after this, maybe when you get to wherever you're going, try it then. It's a quick thing just to get it to solidify in your head. The answer is going to be 2x cubed minus 2x plus negative 18x over x squared minus 2. All right, so check that on your own time. I really recommend just practicing it once. Even just one practice problem is better than nothing. Okay, any questions on that? But don't do it now, do it later. That's a surefire way to get it to solidify into your long-term memory. Can I move on? Okay. So now on to the bulk of that was preliminary information. Now on to the rest of it. So the first thing is the remainder theorem, which is not super useful by itself. It's mainly, there's a thing in mathematics, if you get later on in mathematics, you might hear the terminology of a lemma or a corollary. Have you ever heard those terminologies before? Probably not. We usually use it for the high and mighty mathematicians. We start to fun fact, if you do become a math major, you start wearing one of those frilly things that like Shakespeare wore, and you wear a powdered wig, and you want to be you legitimately have to do that. You have to talk in a high and mighty voice whenever you go to class. It's really, really annoying. But that's something we do in those ones. A lemma is a simple theorem. It's a simple fact that's used to prove something bigger. And a corollary is a consequence of a theorem. So this really should be a lemma. The remainder theorem is really more of a lemma than it is anything else. And so what it says is if f is a polynomial and you divide it by x minus c, the remainder will be f of c. So This was very, very useful back in the day. Back in the day when we didn't have calculators, because mental math is not too terrible to do, this was a really, really useful way. So it says if f of x is equal to 2x cubed minus 4x squared plus 5x minus 3, find f of 2, f of negative 2, rather. So option one, now that we have calculators, option one is what I'd recommend, which is brute force. With a calculator. F of negative 2 is equal to 2 times negative 2 cubed minus 4 times negative 2 squared plus 5 times negative 2 minus 3, which will equal negative 45. But I'm like, so that's the way it is nowadays. Now we can just plug it into our calculator and it's all fine and dandy. But imagine you were back in the times of even before Newton. So like in the I think when was Newton? He was 1700s or 1600s. So imagine you're in the 1500s. You don't have a bathroom you don't have modern plumbing or anything like that, and paper is very hard to come by. It's very, very like paper isn't something you can buy at the street. You have to have a like it's very, very difficult. You have to make it with that whole like those mesh things. You have to like wet it down and make your own paper. It's very, very annoying. So trying to use paper to figure out all these multiplications is not in your best interest. But option two is to use the remainder theorem with synthetic division. So what the remainder theorem says is if you want to know f of negative 2, divide f by x minus negative c. X minus c. So in this case, divide it by x plus 2. So negative 2 divided into 2x cubed minus 4x squared plus 5x minus 3. Notice that all powers of x are present and accounted for, so we don't need to put any placeholders. And so these are pretty small numbers to work with. So bring down the 2. I could write this in the dirt with a stick, and it wouldn't be too terrible to do. So negative 2 times 2 is negative 4. Negative 4 plus negative 4 is negative 8. Negative 2 times negative 8 is positive 16. 5 plus 16 is 21. Negative 2 times 21 is negative 20, or negative 42. And we get negative 45. That right there is f of negative 2 by the remainder theorem. Now we'll move on before anybody questions whether or not synthetic division existed back then. So why is this even relevant? Because synthetic division didn't come out until like the 60s, 1960s or something like that. I don't remember when it came, when somebody figured it out. But you would have been doing long division anyways, or you would have been doing long division, so it would have been really tedious anyways. So honestly, my best guess as to why we still teach about the remainder theorem at all is just to get more practice with synthetic division. That's the reason why. But it is useful for the next things. The reason why it's here, honestly, is it is a lemma. It is a small result that is used to prove the factor theorem. If f is a polynomial, then f of c equals 0 if and only if x minus c is a factor of f. The factor theorem says that if f of c is equal to 0, then that automatically means that x minus c is a factor, and vice versa. We already knew the backwards direction. We already knew it was kind of immediate that if x minus c is a factor, then f of c is equal to 0. That's pretty clear. right? If, for example, like you don't need to write this down, but if f of x is equal to x minus 1 times x squared plus x minus 3, it's quite clear that if you plug in 1, f of 1 is equal to 0, right? Because if I plug in 1, that becomes 0, it wipes the whole thing out. But the reverse direction, the forward direction, in fact, for us, is very, very useful. This direction is very useful. What it tells us is that the zeros, this means the zeros slash roots make up the factorization. That's what it's telling us, is that if you know that f of c is equal to 0, which we can do fairly quickly now with a calculator at our disposal, right? It doesn't take too much energy to plug in -5, so on and so forth into the calculator. When you plug those numbers in, it's not too terrible. If you know it equals 0, you automatically know the factorization that it's a factor. That's pretty useful when it comes to going back to what we did last time, right? Trying to figure out how to graph a polynomial is a pretty big deal. And you need to know how it factors in order to find the zeros and their multiplicities. So for this one, is x plus 5 a factor of f of x equals that? Well, if it were, if x plus 5, which I'm going to write right beneath it, this is x minus -5 because we're going to use synthetic division here in a second. If that was a factor, then then f of -5 would equal 0. If it was a factor, then by the factor theorem, f of c would be equal to 0. Now, we can do a calculator to do that, to check it, or I have a reason for doing this. We'll use the remainder theorem to check this. Because reasons. Um, Normally, I would just say check it in your calculator. Plug in -5 into that, and you'll see that it equals 0. But I have a reason for this. I want to show us something that's going to be useful for the next page. So -5 synthetically divided into 2x to the fourth. All powers of x are present in that, right? X to the fourth, x cubed, squared, first power constant. Good. So 2x to the fourth, 12x cubed, 6x squared minus 5x, and plus 75. Let's put a vertical bar right before the constant term. Go ahead and perform the synthetic division yourselves. I'm going to pause it, and then I'm just going to have the whole thing present after the fact. So people watching the recording, you should do it on your own. If you're stumbling with it, go back and look at the synthetic, go back in the video. All right, so this is what you should get for the synthetic division. You should get 2, 2, -4, 15, 0. So by the remainder theorem, this is your remainder. With synthetic division, the number that appears right in this bottom right corner, that is your remainder. So f of -5 equals 0, which means that yes, x plus 5 is a factor. Because f of -5 equals 0, that means that it is a root or a 0 of the function, meaning that x plus 5 is a factor. And in fact, this is the reason why I wanted to mention this. In fact, f of x could be rewritten as x plus 5 times 2x cubed plus 2x squared minus 4x plus 15. I didn't mean to box that in. I changed my mind. So in fact, because you get a remainder of 0, you can now realize that f of x has this factor that we just figured out was a factor times the quotient that we got when we did the long division, or the synthetic division, but long division also. Is that okay? Any questions on that? All right, let's take our break. Let's come back at 1:05 to finish this off. And then how many more pages do we have? But anyways, we'll come back at 1:05. People watching the recording, go do some guided meditation. So we're back, and then we're going to go ahead and make this realization into a theorem. So they usually have in every textbook they have like it's not a theorem, but it's like a bunch of different ways, analogous ways to say the same thing. And it's very, very similarly related to the factor theorem. So I decided to make my own one called the Big Boy theorem, right? To make sure I'm hip and with it, right? That's not Black Ops 1. That's not Call of Duty Black Ops 1. That's boy, right? We still saying that, or is that 2000 and late? No, we're not saying boy anymore like that. Okay, unfortunate. I like saying boy. Okay. Let f be a polynomial and c be some real number. If one of the statements is true, then all of them are true. So that means if you know any one of these things, you know all of them, which is pretty awesome. And so the first one is that f of c is equal to 0. If you know f of c is equal to 0, that automatically means by the factor theorem that x minus c is a factor of f. That's the factor theorem. That's already done. That was an if and only if statement. Now we have another one. The next one says that f of x is equal to x minus c times blah, where this is the quotient from dividing by x minus c. So if you know that f of c is equal to 0, you automatically know that f of x is equal to x minus c times another factor immediately. Then another thing is that you know that x equals c is a 0 / root of f. Now that one is kind of, that's just by definition, right? So I'm combining a bunch of theorems and definitions into one big boy theorem. And so if f of c is equal to 0, by definition, that means that x equals c is a root. And then the last one, least important, is that f of x divided by x minus c has remainder 0. This is the most useful part. The first three. The other two, the bottom two, are good. They're useful in short conversations with people, but otherwise, the first three are the best. So, as an example, if is x minus 1 a factor of f of x, and what about x plus 2? So, the first factor that I've mentioned, x minus 1, if it was a factor, then it would have remainder 0 when I did synthetic division. And same thing with x minus 2. So let's go ahead and do that. So for x minus 1, what's the c value? Is it 1 or is it -1? Don't answer. Let everyone get a chance to think. Synthetic division is x minus c. So what's the c value? 1. Just 1. So we'll put a 1 here and see if when we divide it And notice that all powers of x are present. So we don't need to do any placeholders. 2x cubed minus 1x squared plus 2x minus 3. If it were a factor, then when I divide, I should get a remainder of 0. So bring down the 2, multiply diagonally and add vertically. 1 times 2 is 2. Negative 1 plus 2 is 1. 1 times 1 is 1. 2 plus 1 is 3. 1 times 3 is 3. Negative 3 plus 3 is 0. So you get a remainder of 0. That means that it is a factor. If you get a remainder of 0, that means that there was nothing left over when you divided by it, meaning that it is a factor of the number. And there's remember that all numbers are polynomials, just very, very boring ones, right? So it's the same thing that's going to be true when you do, don't write this down, but if I do 2 divided into 104, 2 goes into it nice and neat. It goes into it 52 times with a remainder of 0. And another way to say that statement is that 104 is equal to 2 times 52. So whenever you get a remainder of 0, that means that that's one of the factors. So that's the analogous version with numbers. Maybe that helps you see it better. I'm not sure, but either way. So yes, it is a factor. The answer is yes. And in fact, f of x can be rewritten as x minus 1 times 2x squared plus x plus 3. Because it should be equal to, by this big boy theorem, if you know that it's a factor, then f of x is equal to x minus c, in this case, x minus 1, times the quotient that you get when you do the long division or the synthetic division. Next one. For x plus 2. Let's go ahead and check to see if it synthetically divides nicely, if we get a remainder of 0. Another way is to find f of negative 2 in your calculator. If f of negative 2 equals 0, then yes, by this statement up here. If f of c is equal to 0, then x minus c is a factor. So that's another way to show the same thing. But I'm going to do synthetic division because if it is, it might be nice to write the factorization. So negative 2 this time, because in order to use synthetic division, it needs to be of the form x minus a number. That's writing it as x plus 2. So we need to rewrite this as x minus negative 2. And then do the synthetic division. So 2x cubed minus 1x squared plus 2x minus 3. Draw a vertical line right before the constant term and perform the synthetic division. Go ahead and do it yourselves. I'm going to pause the recording. You should do it as well. Okay. You should get negative 27 as your remainder. As that is not 0 by the big boy factor theorem above, that means that it is not a factor. You have to say it that way too, by the way. When you're writing on the exam, you need to explain it on your work and say by big boy. You gotta add a bunch of them too. The more you do it, the more you have to write it. The more I's you have to write. No, I'm kidding. You don't need to justify. You've learned it in the class. You don't need to justify. But anyway, so the answer is because it does not equal 0, it's not a factor. Now on to the real use of this thing. This was just an extra problem to add in for funsies. The next one is the way I like to use it. So factor m of x equals 3x to the 4th minus 11x cubed minus x squared plus 19x plus 6, given that m of negative 1 and m of 3 are equal to 0. Now, if you remember, we've only learned how to factor quadratics and a few niche situations when it comes to higher degree polynomials. We only learned how to factor with the AC box method and those things, and those only work with quadratics. So how do I factor something like this? Now, there's a way to do it that we'll learn in the next section, which we should hopefully get to and probably not finish. I think I was a little bit ambitious when I decided that in this calendar. Did I really think that we could do that in one day? Yeah. So, all right. Uh, we'll see how that goes. But either way, unless you're given some information about it, there's no way to do it. There's no quartic formula. There's a quadratic formula, but there's not a quartic formula. There's not a quintic formula. So finding those things is a little bit difficult. However, for this problem, since m of -1 equals m of 3 equals 0, that means by the big boy factor theorem that x plus 1 and x minus 3 are factors of m. So that means by the big boy factor theorem that if we synthetically divide by x plus 1, meaning that our c value would be -1, if we synthetically divide, whatever we get as the quotient, that'll be a factorization of it. That'll break it down by 1 degree. So let's go ahead and do that. We can start with 3 or we can start with -1. It doesn't really matter. I'm gonna do -3 or -1. So -1 synthetically divided into, notice that all powers of x are present. 3x to the fourth, -11x cubed, -1x squared plus 19x plus 6, vertical line right before the constant term. Go ahead and do this one yourselves and pause the. I'm going to pause the recording. I'm also going to write something else down below this. Don't write that down. So I'm going to write that in a different color. So I'm going to pause the recording now. Okay. So don't disregard the red thing for people watching the recording. So you should get that you get a remainder of 0. That is true because we already knew that m of -1 and m of 3 equals 0. So if we didn't get 0, we have made a mistake somewhere. But we did, and so that means by the big boy factor theorem that this is going to equal x plus 1, because your c value is -1, so it's x minus -1, or x plus 1, times your quotient that you got, 3x cubed minus 14x squared plus 13x plus 6. Now, a classic mistake that students will make on this problem is then they'll do the same thing with 3 to the same polynomial. But that doesn't break down like that just writes it in a different way as a product of x minus 3 times 3x squared cubed minus 2x squared minus 7x minus 2. It doesn't factor it any further. We want to break this down into a bunch of linear factors. We want to write it as x plus 5, x minus 10, whatever it may be, just a bunch of those. So how do I break it down further? How do I do that? Here's the answer. This piece right here. Since x minus 3 is a factor of m, it must be a factor of this by necessity. So write that down and then we'll say so I'm doing what I don't like in math textbooks, which is where they say this is left as an exercise to the reader. They do that in a lot of upper division math textbooks. They say, this is clear from the context, or this is left as an exercise to the reader, where I'm like, I'm reading a book. I should be given the information. I don't want to figure it out myself. I want it to be right there for me so I can see how you figured it out. Give me exercises after the fact, sure. But anyways, that's just something I disliked when I was a grad student. Anyways, why is that true? Why am I saying that's true by necessity? We know that it's a factor of m. That's what this first line said. So it's clearly not a factor of x plus 1 because x plus 1 is already broken down as much as possible. So it must mean that it goes into this because it has, like, x minus 3 has to divide m. And this is just another way to write m. So it can't divide x plus 1, so it has to divide that. So that's how we'll break it down further. So we'll bring this over and do 3 synthetically divided into that. 3x cubed minus 14x squared plus 13x plus 6. Bring down the 3, multiply diagonally, add vertically. 3 times 3 is 9. Negative 14 plus 9 is negative 5. 3 times negative 5 is negative 15. 13 plus negative 15 is negative 2. 3 times negative 2 is negative 6, which adds to 0. Ta-da! It does work out, as we might expect. Since it cannot divide x minus plus 1, it has to be able to divide that other portion of m. So now we know further that m of x is therefore x plus 1 times this. But I just found out with this synthetic division that you can rewrite this expression as x minus 3 times 3x squared minus 5x minus 2. Now we're left with just a quadratic, and we know how to factor quadratics. We can use the AC box method, bottoms up method, any method that you really want to use to factor it. But in the interest of time, I'm going to do it for us. This factors to x plus 1 times x minus 3 times 3x plus 1 times x minus 2. That is the full factorization of m of x. Any questions on that? Okay. Ooh. So we got 25 minutes. I don't think we're going to be able to get through a whole section in 25 minutes. And we have 2 more problems to do. So that'll bleed over, which means that our homework for 2.4 will be extended. The good news is that 2.4 is a relatively fast section. So we should be able to get through it pretty quickly after the fact. So example 2.3.7, can create the equation of a polynomial that passes through the point negative 2, 100, whose zeros and multiplicities are listed. Okay, so we know the zeros, we know their multiplicities, and therefore, by the big boy theorem, f of x will equal, leave a little bit of space, and then write x plus 4 to the first power, because we have a 0 at negative 4. So we have x minus negative 4. And it's going to be raised to the first power because the multiplicity is 1. Then times x plus 1 raised to the third power. Then times x minus 0 to the first power. Then x minus 2 squared. Make sure you left that space in front of the x plus 4, though, for a reason. We're going to write an A there for some number A. And we're going to write this. Any polynomial, or like any value of A, will have these zeros with multiplicity. So let's write that down, and then I'll explain what I mean. Any polynomial, I can put a negative 5 billion, I can put a 2, I can put a pi. I can do whatever I want. And this function will have those zeros to those multiplicities. However, we want a specific a value such that when we go through, like when we plug in x equals -2, we get a y value of 100. So there are infinitely many polynomials that have these zeros and these multiplicities, but there is only one polynomial that has those zeros and multiplicities and goes to the point -2, 100. So, however, we're given that f passes through -2, 100. So what was my theorem? What was Phil's theorem? My super humble, I decided to name it after me because I'm so humble. If you know that your function passes through the point -2, 100, what can you say about f of -2? It's equal to 100. This means that f of -2 is equal to 100. And this allows us to solve for a. I told you that that theorem is so important. It's central to your understanding of functions. If you pass through the point -2, 100, you know automatically that f of -2 is equal to 100. So we can use that to our advantage to find our specific a value. Let's do that right here. F of -2 is equal to a times -2 plus 4 times -2 plus 1 cubed times -2 minus 0 times -2 minus 2 to the fourth, and that equals 100. How long is section 1.2.4? Did I not bring it? Oh yeah, I didn't bring that. It's not, no, it doesn't matter. That's right, because I've changed it up. I've changed up how I do 2.4 because I found a faster way. Excellent. And if you plug that into your calculator, just be careful with the negatives. Make sure you're careful with the negatives, but you should end up getting 64a equals 100. Which means that a is equal to 100 over 64, which reduces down to 25 sixteenths. So we have our a value, and so we have to jump through one more hoop and rewrite it with the correct a value. So f of x is equal to 25 sixteenths times x plus 4 times x plus 1 cubed times x minus 0, which you can just write as x if you really want to, times x minus 2 squared. And that is our answer. So to recap this problem real quick, any polynomial that has x plus 4 times x plus 1 cubed times x minus 0 times x minus 2 squared will satisfy that condition, the zeros and their multiplicities. But there is only one, so if you have any a value here, that will satisfy them. But there's only one a value that satisfies that point. And we found it here. Okay? I'm going to start this problem off for us, and then we'll finish it. You guys can finish it. So This time, instead of being given the zeros and their multiplicities, we're given the graph. And then one thing I'm going to mention is that there is a solid dot right here at 0, -4. That'll be useful in just a moment. Okay. Well, in the previous problem, I was given the zeros and their multiplicities. I don't have those. Yes, I do. I do, just in a different way. It's tomato, tomato. This is just a different way to say it. We have the zeros. The zeros are -1, 2, and 4. What's the multiplicity here? Is it even or odd? Even, because it bounces. Even multiplicity because bounce. Let's assume 2. Did you notice that the question said find a possible equation for G? Because there are many situations. Without too much context, without knowing multiple points on this graph, there's no way to really know if this is going to be the second power or the 4, like a multiplicity of 4 or a multiplicity of 10 or a multiplicity of 200. There's no way to know. But choose the smallest number you can just to make it easy. You can, like, if you want to on an exam, if I give you that problem on an exam, you can definitely put the 200th multiplicity. You can totally do that. It's allowed. Just let you know that your A value will be very, very nasty. Because if you have the 200th power, it's going to be very, very large. But either way, then this one at 2, is that even or odd multiplicity? Odd. But because it has more jaggedness than the one at 4, they're both odd. Like the 0 at 2 and the 0 at 4 are both odd multiplicities. However, because this is wiggly, this is a little more jagged, it's going to be a higher multiplicity, higher degree. So odd multiplicity with jaggedness. So let's assume multiplicity equals 3. So it has a little bit of wiggle, but you could also make the multiplicity 5 or 7 or 301. It's your choice. Because it's just a possible equation. And then last but not least, this has odd multiplicity with no jaggedness. So let's assume the multiplicity equals 1. It could be that this thing is just really, really messed up in its scaling, and that if you were to zoom in really, really far, that it ends up looking like this actually, and you just can't see it. That could be the case, but we're gonna not assume that unless absolutely necessary. Okay? So we know it has 3 zeros. We know their multiplicities. So it's just like the previous problem. We have the zeros and the multiplicities. So once again, we can do this setup. We now know, therefore, that f of x, or g in this case, g of x will equal a times x plus 1 to the second power. Let me put a purple 2. Second power times x minus 2 to the third power times x minus 4, the first power. Any questions on that? Now the only thing left to do is to solve for a. And how do I do that? Usually, and so I stole this graph from somewhere else. So it doesn't have my Desmos graph style, but if I were to make one on the exam, I would make sure to plot the point that I wanted you to use. There is a y-intercept at -4. This point right here, g of 0 equals -4. Use to solve for A. I'd like you guys to finish the problem off on your own time. It shouldn't take too much more. Just plug in 0, set it equal to -4, and see what A value you get. You should get -1/8. So you should get this, -1/8. So when you're checking it later today, go back through this problem again. It's a good idea. It's a really good idea. This is a very, very good critical thinking problem. I love this problem. It's my favorite one in this section of the notes. The previous one is fun. This one's more fun. Phil, you and I have a different definition of fun, I'm sure. Yes. But so you get -1/8. And that kind of aligns, right? If you look at the multiplicities, if you add them up, 2 + 3 + 1, that's degree 6. Notice that the end behavior is falls on the left and falls on the right. So it should be an even degree polynomial, and it is. And because they're both pointing downwards, your coefficient should be negative, and it is. So cool situation. This challenge problem is also a great one for this weekend. Instead of playing, Yahtzee or Settlers of Catan with your friends and stuff, or not Settlers of Catan if you don't like that one. It's kind of it's played out. We've already seen it. Maybe play I don't know, Dominion. Isn't that a game? Isn't that a board game? Either way, or D&D. Instead of doing that, bust this problem out instead. Have a good old time with your friends. It's a good problem. Okay. As I said, there will be a video sent out about synthetic division to show why it works in just a little bit. Now on to 2.4. The fundamental theorem of algebra. You'll see that a lot in mathematics, the fundamental theorem of blank. There's a fundamental theorem of calculus. There's a fundamental theorem of arithmetic. There's a fundamental theorem of probability. There's a fundamental theorem of geometry. There's a bunch of them. And when they say that, it means that it's so central to everything that it's very, very, it needs to be mentioned that it's so fundamental. And this was discovered by Carl Friedrich Gauss, very famous mathematician. You probably have heard of him, even if you haven't. He's basically got his fingers in everything. He was considered the last mathematician who knew everything. Because as we've gone on in time, we've learned more and more about life, right? We've learned we keep adding more and more to our knowledge. And so nowadays it's impossible to know everything about mathematics. You have to pick a specialty. But Gauss was very, very famous. He knew everything. He was very, very prolific. He's got his theorems in mathematics and in physics, maybe even in some in chemistry, I think. Guy was crazy. And his theorem said that if f is a polynomial of degree n, then it has at least one zero or root. Amazing. Amaze, right? Wait, where's my note? I forget what I wrote here. What I wrote. There it is. Okay, cool. That is the theorem, but the corollary, the result is far more important. And it says, as a consequence, all polynomials can be factored into linear terms. That is, f of x equals a times x minus c sub 1 times x minus c sub 2 times ... times x minus c sub n. Let's write that down and then we'll understand the implication of that statement. because while it doesn't seem like a big deal, it is. And I'll explain why. Because in mathematics, we're very, very concerned with whether or not things exist. And so what this theorem says is that every polynomial, no matter what polynomial you can think of, you can think of any symbol, any of them, and you can add any number of coefficients. They could be all irrational coefficients, square root 2 x to the fifth minus something or whatever. So those say c sub 1 minus c sub 2 minus c sub 3 and so on and so forth. Any polynomial you can think of can be factored, which is really, really useful. That's a big deal about polynomials. Every single one of them can be factored. How it can be factored is up in the air, but we do know that it can be factored. That's not necessarily true with everything else. Other functions like we haven't gotten into logarithms and things like that, but it's not as cut and dry for every other thing where the zeros or the roots of that function are. But with polynomials, it can be done. So I've got an example here. 2x to the fifth minus 5x to the fourth minus 12. It all factors down into this. Which, that has some complex zeros, yes. But it's just like, so that's just going to show you how the theorem actually works. You have to extend yourself. In order to break it down into purely linear factors, it has to be, you have to go into the complex plane. And so, with that knowledge that everything can be factored, let's look at a motivating example. In that previous section, we had this polynomial, capital M, and we were given that fact. But what if we didn't know that? How would we factor that polynomial? Gauss told us that it can be done, but how? And mathematicians have struggled with that for a long time. There are many different ways. There's many different criteria that we've created over the years. One of them is called Eisenstein's criterion. Not Einstein, but Eisenstein. Strangely enough, weird mathematician who's very, very similar name. But that's a graduate level or an upper division math, like a senior level math course concept. But there is one that we can learn about, which is called the rational zeros theorem. Let f be a polynomial with integer coefficients. The rational zeros theorem only works with integer coefficients. That is, f of x is equal to a sub n x to the n all the way down to a sub 0, where a sub n through a sub 0 are integers. Then, if it does have real zeros, they will be of the form x equals p sub 0, plus or minus p sub 0 over q sub n, which I'm going to rewrite as plus or minus factors of a sub 0 over factors of a sub n. So, if it does have real zeros, then they're going to be of the form plus or minus a factor of the constant term divided by the factor of the leading coefficient. Now you're probably looking at this picture and wondering, why the hell is that there? Why is there a toucan with a graduation cap and a pencil? That was made by AI, which is fun. But so this is actually a fairly well-known toucan. You might know his cousin, Toucan Sam, right? He follows fruit, the flavors of fruit wherever they grow, right? He follows his nose. This is his long-lost cousin, so remember, Toucan Sam. I know it's technically Pucan, because QN would make a kun sound, but Toucan. Toucan instead of Toucan Sam. That's my way to help you memorize it. I can't think of a better way to do it. I've looked everywhere. I couldn't think of anything better, so I created Toucan Sam. Toucan Sam's lost long brother or cousin, but it doesn't matter. But anyways, that's the way you can help remember that it has to be factors of a sub 0, p sub 0 to remind you constant term, q sub n to remind you a sub n. So let's go ahead and see how this theorem gets used in practice. And once again, we've only got 3 minutes left, so we'll pick this up on Monday of next week, and the Unit 2.4 homework will be extended. So with 3 minutes, 3 minutes, that's not enough time to go through this problem. So let's go ahead and call it good. We're getting back from break. Let's end it early. Okay, guys. We'll pick this up next time. If you have any questions, please feel free to email me. Please do those problems that we didn't finish, that synthetic division problem, or whatever it was, and then this one. Please do those yourself to get some more practice with it. And have a great rest of your day, a great weekend. Remember that social media is not good for you, and doom scrolling is even worse. It's going to destroy your brain, so don't do it. And have a great weekend. See you then.